तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
While discussing the applications of Laplace transform technique, we introduced ourselves to the concept of system function. We said a system function is basically the ratio of the Laplace transforms of the response to the Laplace transform of the excitation with 0 initial conditions in the system. Now, a system function defined for a particular network is more commonly known as a network function. So, network function is nothing but a system function applied to a particular network, and the network function is defined for a particular pattern of excitation and response. Now, while dealing with networks, there we normally deal the variables of interest to us are voltages and currents. Therefore, it turns out that a network function is the ratio of the Laplace transform of a current or voltage response to the Laplace transform of a current or voltage input. So, in this and the next couple of lectures, we will be discussing special types of network functions applicable to the commonly occurring types of networks that we deal with, and we would like to study the special properties of the various network functions that we are going to define and discuss. Let us see. So, broadly speaking, a network function is the Laplace transform of response which is either a current or voltage by the Laplace transform of the input or excitation which is again a current or a voltage. And this is done with 0 initial conditions. With 0 initial conditions. So, if we call a network function by the general name HFS, it is the ratio of the Laplace transform of a voltage or a current to the Laplace transform of a current or voltage. So, depending upon the so this is in general a polynomial Ps over Qs or Gs over Fs, the ratio of two polynomials, and depending upon whether the response is a current or voltage or the input is a current or voltage, the dimensions of HFS will be either an impedance or an admittance or a pure ratio. Therefore, as far as this is concerned, GFS, it could be an impedance. So, it is called, then in that case it is called an impedance function. It could be an admittance, it is called an admittance function, or it could be a ratio. If the response is a current and the input is a voltage, then it would be an admittance function. If the response is a voltage and the input is a current, then it becomes an impedance function. If both the response and current, are input are both currents, then it is a ratio. If both the response and input are voltages also, then it is a ratio. We call them impedance function rather than impedance because this is a function of S. So, whatever suppose is Z, we can call it Z of S. Similarly, Y of S, this is some ratio as a function of S. These are all functions of S, therefore they are called impedance functions or admittance functions, but loosely speaking we refer to them as impedance and admittances as long as there is no misunderstanding. A second point to observe is that f of s equals 0, the roots of this equation, which are the poles of h of s, represent the natural frequencies of the network. Of the network, a property that we had already discussed in our earlier lectures. So the natural frequencies of the network are given by the poles of h of s. Now the natural frequencies of a given network are unique no matter how you excite the network and what type of response you measure. Therefore, for a given network configuration you have the same natural frequencies no matter what response you take and what input you insert into the network. Therefore, it stands to reason that the poles of network functions defined for a particular network will be more or less unique, with minor exceptions here and there they are unique. So let us say that we are having a network like this. Suppose this is a basic form of a network. Basic form of a network. Now, when you introduce a voltage source as an excitation, you must introduce in such a way that when the voltage is made equal to 0, the basic form of the network is obtained. Therefore, you should introduce a voltage source, for example, by cutting into this and placing a voltage source here. I will explain that what happens if you don't do that. Let us say, so for voltage excitation we will have the basic form would be, suppose you introduce a voltage source here and then so this is, suppose this is Vi, a voltage, all functions of S. This is Laplace transform of the voltage source that is introduced here. So we will call this voltage excitation. So when you introduce a voltage excitation, you must make sure that if the voltage is made equal to 0, that means this is short circuited, the original form of the network is obtained. If you had put a voltage source here, then the voltage is reduced to 0, this is short circuited. Therefore, the original network is modified, it is not the same network as before. So if you introduce a voltage source and would like to find out the natural frequencies of the network, it should be done such that the voltage is introduced into one branch in series. So it is referred to as Pliers type of entry. Pliers type entry. That is, you take a pair of cutting pliers, cut this wire open and insert that voltage source. So this is usually referred to Pliers type entry. On the other hand, if you want to introduce a current source, then the thing to do would be to introduce a current source in parallel with a particular element. Let us say this is the current source. So II of S. So this is all we are talking in terms of Laplace transforms. Let us say II of S. So that when the current strength is made 0, that means this is open circuited, you get the original basic form of the network. So when you introduce a current excitation, then the entry is said to be a soldering type of entry. That is, you take the current source and solder the leads to these two nodes. So this is the basic distinction between how you introduce a voltage excitation and a current excitation into a basic network. The principle is that when you reduce the voltage to 0 or replace it by a short circuit, or the current excitation to 0 or replace the current source by an open circuit, the original basic form of the network is obtained. So when you do that, no matter how you introduce excitation into what branch, whether current or voltage, and find out the response at any other point, then the poles of the whatever network function you are talking about will be more or less the same, because the basic form of the network remains the same. So this is important to keep in mind, that for a given network configuration the natural frequencies are unique, and therefore no matter what type of network function you define, the poles are likely to be the same. I said more or less, and I also said with minor exceptions. Sometimes some minor exceptions arise, because sometimes the poles can cancel out with zeros, leaving some of the poles may not be present in particular network functions, but by and large before the cancellation takes place all the poles will be the same. Now we also want to make a distinction here between what is called the driving point function. The driving point function is obtained the ratio of response to current when both the response and current are associated with the same terminal pair. So if you are, for example, if this is II and I want to find out the current response in this, say IYFS, so the ratio of IYFS by VIFS, this is the current and the voltage are associated with the same terminal pairs, with the same terminal, then it is called a driving point function. In this case it happens to be a driving point admittance. In this case, suppose I have this Vy, so I am measuring the voltage across this node, the Laplace transform of the voltage, that is what is meant by Vy, and the ratio of that to IIFS, so Vyfs over IIFS, this is a driving point function. In this case this happens to be a driving point impedance function. On the other hand, a transfer function is associated with the ratio of a response which is measured at a different pair of terminals, not necessarily at the driving terminals. For example, if I take, this is the voltage and I take the current here Vz, I am sorry, the voltage across these points. So this the response is measured across this pair of terminals, the voltage is introduced here, both of them are not associated with the same pair of terminals, then Vz by V of S by Vi of S is a transfer function. It is actually a transfer ratio because the ratio of two voltages. Let me say that if I measure the current here Ip, then Ip of S divided by Vi of S is also a transfer function, because the current is measured in a different branch than the branch in which the voltage is introduced. The terminal pair associated with the voltage source is different from the terminal pair which is associated with the current Ip. So this will be a transfer function, and this in this case is a transfer admittance. In the case of a current excitation, suppose I measure this voltage Vq, then Vq, response Vq divided by this current II of S is also a transfer function, but in this case it happens to be a transfer impedance ratio of voltage to a current. Let us say I am interested in finding out this current as the response, IR of S here, then the ratio of IR of S to the input current II of S is again a transfer function, which is now a transfer current ratio. So in general we have different types of these network functions. Some are driving point functions, some are transfer functions. The driving point functions are associated, both the response and excitation are associated with the same terminal pair, and therefore since one has got to be the current, the other has got to be voltage, then the driving point functions are either impedance functions or admittance functions. On the other hand, transfer functions, you have all possibilities. The response is measured at a different pair of terminals compared with the excitation, and depending upon the quantities that are involved, transfer functions can have the dimensions of impedances, admittances, or pure ratios. This is a transfer voltage ratio, this is a transfer current ratio, this is a transfer admittance function, this is a transfer impedance function. So this is the general way in which we define network functions, but we would like to talk about these network functions for particular categories of networks which are important. But before that, we would like to talk about one other concept. Now, a network is said to have, suppose you bring out some terminals from the network, then we introduce the concept of a port. Port is defined as a pair of terminals in a network through which a signal is either accessed to the network or from the network. That means whenever you introduce a signal into the network or take out the signal from the network, then it is said to be a port. So port is a terminal pair through which a signal is accessed to or from the port, from the network. So when you want to introduce a voltage source to the network, you introduce the terminal pair, that is called a port. Now, suppose you have a network with two terminals, then this is called the port associated to this network N. This is called a one port network. So when we are dealing with one port networks, we are mainly interested in the voltage and the current relations of this network. So in Laplace transform domain, this is Vs and Ifs. So the ratio of the voltage to current or current to voltage is what we are interested in. We are not particularly interested in what is happening inside. So we are interested in the behavior of the terminals, and this is called a one port network. That means this network is connected to an external source to these two terminals, and the response is also measured at these terminals. This is also called a two terminal network. Also called one terminal pair network. All are one and the same. One terminal pair network. We can extend this concept to, for example, a two port network. So a two port network is represented in this fashion. It has got two ports. Normally labels are given 1 1 prime, 2 2 prime. This is called port 1, and you call this V1 and this as I1. Now here afterwards I will drop the functional notation function of S, because we understand that all these voltage and current that we are going to talk about are Laplace transformed variables. Therefore it is needless to specify that is V1 of S and I1 of S. It simplifies if you write V1 and I1, but you understand that they are Laplace transformed variables. So this is V2 and this is I2. So this is port 1 and this is port 2. So we define the two ports separately as the two terminal pairs. This is called a two port network. Two terminal pair network. We do not call it a four terminal network. You must be wondering why. See, a four terminal network, suppose you consider this as 1 2 3 4 terminals, then in a four terminal network, we understand by a four terminal network that you can connect excitations to the terminals in an arbitrary fashion, and you can measure the response in arbitrary fashion. But as far as two port network is concerned, if you want to introduce an excitation in the network, you have to connect this either to this terminal pair or to this terminal pair. We cannot connect an excitation across these two terminals or these two terminals, nor can we measure responses across 1 2 or 1 prime 2 prime. So if we understand clearly that any method of inputting a signal into the network or measuring the response will be associated with specified terminal pairs, either this terminal pair or this terminal pair, but no other terminal pair, then it is definitely a 2-port network. So a 4-terminal network is a more general type of network configuration, but when we talk about 2 terminal pairs, we always understand that any input is given to the network either this pair or this pair of terminals, and the response also is measured across this terminal pair or this terminal pair, not across any other terminal pair. As a result of that, we can always, when the current is introduced here, we can say the return current is always equal to I1, whatever, because after all when you connect a load or a source here, this current returns like this. And similarly, if this is I2, this is going to be I2. In a 4-terminal network, that condition need not be valid. So let me illustrate that here. Suppose I have a 4-terminal network. This is 1 2 3 4, I1, I2, I3, I4. There is no guarantee that I1 equals minus I2. All we can say is I1 plus I2 plus I3 plus I4 is 0. So it is possible that you can have a situation by connecting external current sources so that I1 is different from minus I2. You can connect a current source between these 2 points, current source between these 2 terminal pairs, and so on and so forth. So a 4-terminal network is different from a 2-terminal pair network or a 2-port network. We are interested for the most part in this 2-port network in our discussion. Now it also turns out that it is not necessary that all the 4 terminals are distinct. It is possible in special cases that these 2 are the same. In electronic circuits applications, when you filter networks and so on, normally have a common ground through a 2-port network, therefore 1 prime and 2 prime may be identical, in which case it's a 2-port network with a special characteristic that there is a common ground, that is 1 prime and 2 prime are the same, then it's called a 3-terminal 2-port network. But what we have represented here without a connection between 1 prime and 2 prime is the more general type. We simply assume that there may or may not be a common connection, so we will take it a general way that there is no common connection. It's called a 4-terminal 2-port network or simply 2-port network. So that is the distinction between a multi-terminal network and a multi-port network, and this concept can be extended to n ports, 4 ports, 3 ports, and so on. So if you have a n-port network, then you have n terminal pairs, port 1 1 prime, 2 2 prime, down the line to n prime. So port 1, port 2, port 3, port n port. So that will be a little more complicated, but in our discussion here we will confine ourselves to the network functions associated with a 1-port network and a 2-port network. After having discussed the definition of a network function in a general way, let us now consider network functions applicable to 1-port networks to start with. So this 1-port network N is a linear time invariant network. Of course, it is understood it is also continuous time network, usually abbreviated as LTI network, linear time invariant network N, because it is only for such networks we have a proportionality relationship between the Laplace transforms of the voltage and current. So here if I introduce a voltage excitation to this network at port 1, there is only 1 port here, of course 1 1 prime are the 2 terminals, then the response is the current. The ratio of the Laplace transform of the response to the voltage is called YFS. This is called the driving point admittance function of the N port of the network N, driving point admittance function. It is a function of S. It depends upon the constituents of the network N, various R, L, C elements, their values and so on. It is a function of S, that is why it is called driving point admittance function. but loosely speaking we will simply refer to this as admittance itself, implying that it is also a function of S. We do not specifically mention that it is y of S admittance function, we usually write y itself, but strictly it is y of S. Now on the other hand, if we introduce a current excitation to the network through a current source and measure the response, voltage response, and find the ratio of the response to the excitation in transform domain, then you get Z of S, V1 of S, I1 of S. This is called the driving point impedance function. The idea in defining these functions is that if we know y of S, you can calculate the response for any voltage input. You know the current, because after all I1 equals y times V1 of S. So for any other excitations you can immediately find out the current. Similarly, if you know the current excitation, you know the voltage for the corresponding current excitation knowing Z of S. So the idea is we do not have to find out the internal construction of the network. Once we know the y of S or Z of S, we know the terminal properties. For the given current you know what is the voltage, for a given voltage you know what is the current. Now it is also obvious that once you have two terminals here, when you measure the admittance of that must be the reciprocal of the impedance. So after all the ratio of V1 to I1 here must be the same as the V1 to I1, because whatever be the constituents of the elements at the terminals, the impedance must be the same. So when you have got for example an inductance here, it is a pure inductance, V1 of S by I1 of S is Ls. Similarly V1 of S by I1 of S must be Ls. Therefore it stands to reason that y of S and Z of S are related in reciprocal fashion. Ys times Z of S is equal to 1. So one is the reciprocal of the other, but the way in which it defined is different. So we also said any network function, the poles of the network function are the natural frequencies of the network. So the poles of y of S are the natural frequencies of the network when network N has the excitation removed. So if V1 is removed, that means V1 is replaced by a short circuit. That means the poles of y of S are the natural frequencies of the network N when the two terminals are shorted. So poles of y of S are so called short circuit natural frequencies. That means this network N, suppose you short circuit the terminals, and for example a capacitor inside the network, you charge it and let it go, then whatever oscillations, whatever complex frequencies are present in the various responses are the natural frequencies. So the poles of y of S are the short circuit natural frequencies. On the other hand, when you come to Z of S, this is also a network function. The poles of Z of S represent the natural frequencies. But what are the natural frequencies? Suppose the current source is removed, that means these two terminals are open. Therefore it is the natural frequencies under these conditions. So the natural frequencies of that network are the poles of Z of S. Therefore you can say poles of Z of S are open circuit natural frequencies. So that is the difference between y of S and Z of S. But we also know that y of S is the reciprocal of Z of S. That means the poles of y of S are also zeros of Z of S, because after all y of S is 1 over Z of S. So the poles of y of S which are also equal to zeros of Z of S are the short circuit natural frequencies. The poles of Z of S which are also equal to the zeros of y of S are the open circuit natural frequencies. That means the natural frequencies of the network with this termination. These are the poles of y of S are natural frequencies of the network with this termination. It is important to keep that in mind. That means as far as ys and Z of S is concerned, both zeros and poles represent natural frequencies of the network under some termination or other. This may not be true in a general case, but as far as one port networks are concerned, both the poles and zeros are the driving point functions represent natural frequencies under the appropriate terminal conditions. So after having defined this, now how do we go about calculating the driving point impedance or admittance of a given one port network? Now all these definitions assume that there are zero initial conditions in the network. if there is no initial conditions in the network, in the transform network, every inductance is replaced by its impedance function, which is LS, generalized impedance function. Every capacitance has an impedance 1 over Cs. Every resistance has an impedance function R. So all the elements inside the network are replaced by their generalized impedances R, LS or 1 over Cs as the case may be, and you try to find out the effective impedance from the looking in terminals, from the terminals of the network, or the effective impedance from the terminals of the network, just as you would calculate the effective resistance of a DC in a resistive network, except that instead of dealing with all resistances, you replace with elements having impedances R, LS and 1 over Cs. So to calculate calculation of driving point functions, admittances or impedances as the case may be. By the way, a general name for impedance or admittance is called immittance. So some people use this. Immittance means either an impedance or an admittance. So a driving point function is an immittance, either an impedance or an admittance. How do we calculate this? In simple cases, you can use series parallel reduction technique. Example, suppose I have a one port network like this. Let us say this is 1 ohm. So 1, this is simply say 1, this is LS, suppose a 1 Henry inductance, therefore this is S. Suppose this is also a 1 ohm resistor 1 and this is 1. Suppose these are all the generalized impedances, then Z of S is 1 ohm in series with a parallel combination of 2 branches. The respective impedances of that are S plus 1 Y by 1 over S plus 2. So this is, if this is the impedance of this is S plus 1, the impedance of this is 1. The parallel combination has an impedance S plus 1 multiplied by 1 by S plus 1 plus 1 S plus 2. So that will be S plus 2 plus S plus 1, 2S plus 3 divided by S plus 2. So that is the impedance function. So we can use the same, this is the same technique that we use in the case of finding out the effective resistance of a DC net, of a resistive network. Same technique that we use here also. To check on the validity of this result, after all, Z of S is generalized impedance function of this network, one port impedance. So under sinusoidal steady state, Zj omega represents the impedance at a particular angular frequency omega. So let us see what happens when S equals 0. When S equals 0, this is 3 by 2. That means the DC resistance of this must be 3 by 2. 1 ohm in series with 2 1 ohms in parallel, because under DC an inductance is short circuit. Therefore 1 in parallel with 1 gives you half ohm resistance, half in series with 1 will be 1.5 ohms resistance. That is exactly what you get Z of S when S equals 0 is 3 by 2. On the other hand, let us say for very large frequencies, when S goes to infinity, that means the omega is going to infinity, j omega is going to infinity. When omega goes to infinity, that means S goes to infinity. For large frequencies, this is a open circuit because the impedance offered by an inductor at very large frequencies is infinitely large. Therefore practically this branch goes out of commission, it does not participate, no current flows through that. So all we are left with 1 ohm in series with another 1 ohm, 2 ohms. So when Z of S, when S goes to infinity is 2, because 2S is very large compared with 3 and S will be large compared with 2. Therefore its ratio to leading coefficients is 2. That means the effective impedance is 2 ohms. That's exactly what we got here. So sometimes it will be useful for us to check on the validity of our answer by looking at the limiting behavior as S goes to 0, which corresponds to DC, and S goes to infinity, which is the corresponding to very large frequencies. Now this is of course a method which suggests itself for simple cases, but in general you will have to use for a general case loop current method of analysis or node voltage method of analysis. I would like to illustrate this by taking 1 or 2 numerical examples rather than discussing them in a general way. So let me say we'll take an example where I'll write it here, loop current method of analysis. So let me take a specific example. So this is a one-port network with two terminals sticking out. This is 1 Henry, so 1 Henry, 1 ohm, 1 ohm, and 1 farad. I would like to find out the admittance of this YFS. To do that, what we do is we have a voltage source, say V1 of S, and you want to measure the current here. To do that, let me assume that there are 3 loop currents here. I1, I2, and I3. I2 and I3. So you write the loop equations of this 3 loop network in terms of the Laplace transformed impedances and admittances. And so first loop, the total impedance in that loop is, the impedance of this is S, the impedance of this is 1. Therefore, I have S plus 1. I write this in matrix form, I1 of S, I2 of S, and I3 of S. Convenient for me to write this in matrix form. So S plus 1 times I1 of S, and the coupling between loops 1 and 2 is to this 1 Henry inductance, and in that both the currents I1 and I2 are oppositely headed, therefore the coupling impedance is minus S, and the coupling between loops 1 and 3 is to this 1 ohm resistance, and the two currents are oppositely directed, therefore by the it should be minus 1. The self loop impedance of loop 2 of this S plus 1 plus 1 over S, and the coupling of loop 2 with reference to loop 1 is once again to this 1 Henry inductance. So that is impedance of that is minus S. These are all impedances, and the coupling between loops 2 and 3 is to this 1 farad capacitor, and both the loops currents are oppositely directed in this, therefore minus 1 over S. And of course on the other side you have the forcing function. For the first loop, the total driving voltage is V1 of S. For the second loop, there is no driving voltage, therefore that is 0, and in the third loop also it is 0, therefore we can finish this. And the third loop impedance is, the self impedance is S plus 1 over S plus 1, therefore S plus 1 plus 1 over S, and the coupling between loops 2 and 3 is minus 1 by S, and the coupling between loops 3 and 1 is through 1 ohm resistance minus 1. So you have this. So if you after all we are interested in finding out I1 for a given excitation V1, therefore we are interested in finding out the ratio of I1 to V1. So if this is the loop basis, this loop impedance matrix, you write I1 of S as the ratio of two determinants. So the entries here are the same as this, S plus 1 minus S minus 1 minus S, S plus 1 plus 1 over S, this is minus 1 over S, this is minus 1 over S, S plus 1 plus 1 over S. And as far as the numerator is concerned, you replace the first column by the forcing function vector V1 of S 0 0 minus S, S plus 1 plus 1 over S minus 1 over S, S plus 1 plus 1 over S, minus 1 over S minus 1. So you observe that As far as the numerator is concerned, this is V1 of S times this quantity, which can be written as delta 1 1 of S, the cofactor of the first element 1 1. And the denominator is the mesh basis system determinant. We can write this delta ms. So if that is so, that is you calculate delta ms and delta 1 1 s for these particular values, and we get y of s as I1 of s over V1 of s, which is obtained as delta 1 1 of s over delta ms. So ultimately then we have y of s is, the denominator is delta ms. This is the mesh basis system determinant, which is called mesh basis or loop basis system determinant. That means the determinant of the loop impedance matrix, yes. And in the numerator, it is the cofactor of the first term in this loop impedance matrix, delta 1 1 of s. So you can calculate this for the particular, we have got all the values here, you can calculate this delta 1 1 here and this, and you can show that this is equal to s squared plus s plus 2 divided by 2s squared plus s plus 1. Again, we would like to check the validity of this, some verify whether this is in accordance with what we expect for small frequencies and large frequencies. Well, yes, suppose we take the DC case, that is yj omega when omega equals 0 will be obtained by substituting s equals 0. It must be, that means 2 Siemens must be the admittance of this network under DC. You see, under DC this capacitor is an open circuit, 1 Henry is a short, 1 Henry is a short, so 1 ohm in parallel with 1 ohm provides you half a ohm resistance or 2 Siemens admittance. That is exactly what we have when s equals 0. For large values of s, this provides you half a Siemens admittance, that means 2 ohms must be the resistance of this network for very large frequencies. So very large frequencies, capacitor is a short circuit, the 2 inductors are open circuits, therefore these 2 are not participating, therefore you have 1 ohm, the path to the terminals are 1, this is a short circuit, another 1, therefore this is 2 ohms. Impedance is presented for the network for large frequencies. That is exactly what we are having here. Now you can also carry out this analysis by node admittance. So you can also have node voltage method for evaluation of the network function. So what you have to do then is, when you want to make the node analysis, the current excitation is more appropriate, therefore you can write here I1 and then the same elements that you are having here. Suppose you take this as the datum node, this is node 1, this is node 2, this is node 3, and you can set up the node basis determinant as follows. I will just give the final result, you can complete the work, because now we are talking in terms of admittances. The total admittances connected to node 1, the admittance of this plus this, the admittance of this is 1 over s, the admittance of this is 1. So 1 by s plus 1 is 1 by s minus 1 minus 1 by s, s plus 1 by s minus s minus 1 minus s, s plus 1 by s, v1, v2, v3, they are all Laplace transformed variables. The current is entering node 1 only, no other place, therefore this I1 0 0. So on this basis, proceeding in a similar fashion as we had in the other case, Z of s can be written as the node basis system determinant. That means the determinant of this matrix, and on the numerator you have delta 1 1 of S, where this is the cofactor, first cofactor of this. So you can calculate it in this fashion, and you would end up with a result which is 2s squared plus s plus 1 divided by s squared plus s plus 2, which is of course the reciprocal of y of s. So you have alternate ways of doing this, either you series parallel reduction, star delta conversion, whatever the whole gamut of analysis techniques that are available to you in the DC networks case can be employed here as well, and you can find out the effective impedance at the terminals of a one port network in exactly an identical fashion. One last example, a quick example. Suppose I have one port network. This is again assumed to be time invariant linear network. On closing the switch at t equals 0, I find that I of t in this case happens to be 2 minus 2 e to the power of minus t. This is known. This network, when I close the switch with 2 volts with 0 initial energy stored in L, has given me this. What I would like to know is, if this network N is connected to a sinusoidal source of cos t volts, I would like to find out the current under steady state. How much is the current? I don't know anything about inside the constitution of the network. So from the terminal conditions I should be able to do it. Now this is the question that is asked. Now if I can find out from the given data the YSF, the impedance function of this network, the current is IT, therefore the response is IT, therefore the Laplace transform of that is 2 by S minus 2 by S plus 1, that is I of S, divided by V of S. What is the input? Input is 2 volts DC, therefore its Laplace transform is 2 by S. So this is V of S, V1 of S, this is I1 of S. If you simplify this, it turns out that it will be 1 over S plus 1. So 1 over S plus 1 is the impedance function of this network. Now we want to find out the steady state current with sinusoidal excitation. Therefore this is the general Laplace transform, the ratio of Laplace transforms. So we want to find out the frequency response corresponding to this. So yj omega, omega happens to be 1 for cos t. So we are interested only not the total response. We can find out the total response by multiplying the Laplace transform of this with y of s, but we are interested only in steady state response. Therefore I am taking only the frequency response function corresponding to this is 1 over j omega plus 1. Therefore this is 1 by root, omega happens to be 1, therefore this will be 1 by root 2 at an angle of minus 45 degrees, which means if you have a cos t, the phasor for the voltage and the current are related by this impedance. Therefore I steady state has got, if it is the amplitude of this is 1, therefore the amplitude of the current is 1 by root 2, and there is a phase of minus 45 degrees, therefore this is cos t minus 45 degrees. So that is the steady state current. You can also use this information to get the total response when cos t is switched in at t equals 0 by finding out the Laplace transform of cos t, multiply this y of s and find out the inverse Laplace transform to get the current. So you can see how the concept of the impedance function or the impedance function of a one port network can be used for finding out the responses to other types of excitations. You can find out, suppose cos t is switched at t equals 0 and you want to find the total current, all you have to do is multiply the Laplace transform of cos t ut with the y of s, find out the corresponding I of s, find out its inverse Laplace transform, then that will give you the total response, of which certainly this will be the steady state part. So in this lecture we have acquainted ourselves with the general nature of a network function. We said it is a network function is nothing but a system function applied to networks to the ratio of the Laplace transform of the response to the Laplace transform to the input with 0 initial conditions in the system, and such network functions are defined only for linear time invariant networks with 0 initial conditions, of course. And then we also introduced ourselves to the concept of a port. Essentially, a port is a terminal pair through which a excitation is introduced in the system or a response is measured. And the distinction between the ports, N port network and an N terminal network has been drawn. And the essential concept of a port is, in a terminal pair, one current is going to one terminal, the same current must return to the other terminal associated with the same pair. It can't be otherwise. And in a multi-terminal network, that particular property is not necessarily valid. Then we went to discussion of the distinction between a one-port network and two-port networks. And then we took for special consideration a one-port network, and we saw in a one-port network the network function that we can think of is the ratio of voltage to current or the current to voltage. So depending upon the excitation, we define the driving point impedance or driving point admittance function. Both are reciprocals of each other. We mentioned that the poles of a driving point impedance function are the natural frequencies of the network under open circuit conditions when the terminals are open. The poles of the driving point admittance are the natural frequencies of the network when the two terminals are shorted. That means if you had a capacitor inside the network charged and let its system go on its own, the capacitor discharges, and then various voltages and currents exhibit some natural frequencies, and those natural frequencies will turn out to be the poles of YFS. And since YFS is related to ZFS in a reciprocal fashion, the poles of YFS are also the zeros of ZFS and vice versa. Then we went to we looked upon the various ways in which we can calculate these impedance functions. I said the entire techniques that are available to you for calculating the effective resistance of a resistive network in the case of DC can be used here, except that we deal with generalized impedances rather than pure resistances. So functions of S are involved associated with each term. We can use the series parallel reduction technique, the star delta conversion techniques, or more generally the loop current method of analysis or node voltage method of analysis. We worked out one or two examples to illustrate the application of this technique. We also mentioned that once we have the admittance function or impedance function known to us, we can find out the response to any other excitation through taking the Laplace transforms of the input multiplied by the network function, finding out the Laplace transform of the response, and taking the inverse Laplace transform. We can also use this to get the steady state response under sinusoidal conditions by taking the frequency, deriving the frequency response function from the given network function by substituting j omega for S and taking the appropriate value of omega. In the next lecture, we'll talk about, continue this discussion in relation to two-port networks.